Hello, everybody. Today, I will introduce my paper, Hierarchical Needs-Based Self-Adaptive Framework for Cooperative Multi-Robot System. So I will separate 5 parts to introduce this paper. First is introductions. And in the real world, actually, we have 2 kinds of the system. One is a natural system, the other is the artificial system, which means the man-made system. The natural system and the artificial system are characterized by apparently complex behavior that emerge as a result of the often nonlinear spiritual temporal interactions among a large number of the components at a different level of the organizations. So actually in our research area, we have 2 kinds of the fundamental problems. One is what is the complexity? So from system theory's perspective, the interaction between and within various elements of the system can be regarded as the complexity. So the individual agent and the element principles acting might lead a system behavior changing. So from my research perspective, we believe the intelligence is a kind of the global behaviors caused by individual agents' the interaction based on its current needs or the entire system utility in specific scenarios. So, and for the related work, we will from 2 kinds of the perspective to discuss. One is the multi-agent system perspective. Some of the earliest pioneered works, especially in the distributed artificial intelligence, the researchers define it or the system of the entity working together to reason, planning, solve the problems, thinking abstractly, comprehend idea and language, and learn. This is kind of the DAI, distributed artificial intelligence. And from the multi-agent system perspective, unlike the distributed robotic systems, it emphasizes a large number of the agents and promote scalability. For instance, by using local communication, which play a vital role in the whole system, building various relationships between each robot to adapt the different environment and situations. So in this paper, we just provide the self-adaptive swarm system and compare with the common MRS framework from the task location and planning perspective. So we solve the 2 kinds of the problem. First is how to decompose the individual robot plans from high-dimensional joint configuration space to low-dimensional. The other is how to design suitable local control laws for each robot to complete the global assigned task efficiently and cooperatively. We have 3 kinds of contribution. One is we design the robot needs hierarchy. This idea just inspired by the Maslow's hierarchy of the human needs law. And we designed the robot needs hierarchy to model the individual robot's motivations in the negotiation process and helping the robots to cooperate with each other. Second, we provide negotiation and agreement mechanisms to solve the conflict between the robots' corporations. And those mechanisms also based on the novel priority queue mechanisms related to the robot needs hierarchy. The last, we designed several alternate operations to decompose the complex task into a series of the simple tasks and action, such as the selection, formation, and routing. The approach part, first we just proposed a framework named the Self-Adapt Swarm System, SASS, which combines the perception, communication, and planning at the multi-robots system, the individual robots level. And we also providing a system mathematic definition of swarm behavior, which allowed us to decompose a particular robot's action, such as flocking, pattern formation, and routing plan, and under the same framework. Our framework have 4 kinds of the module. The first one is the perception, and the second is planning module, and the negotiation module, and the last one is agreement and execution module. So for the more detail, you can just look at the paper. We also provide 3 kinds of the algorithm to help the individual robots to share information, solve the conflict, and cooperation with each other to achieve the common task. So for the evaluation part, we choose to use the common open research emulator core networked simulators. And for the experiment setting, we consider only the lower 3 levels robust needs hierarchy, the safety needs, the basic needs, and the capability needs. And we also compare our approach with the state-of-the-art methods of collision-avoid task allocation, CATA, and we designed the 2 kinds of the scenario. One is the static task assignment. The other is the dynamic task assignment. So for the static multitask assignment, we conduct 10 simulation trial for each priority case in a static task assignment scenario. I can play the simulation experiment for you. As you can see, we have a high energy priority, low energy priority, and combine the task priority with high energy and low energy priority, and also compare with the state-of-art method, CATA. So this experiment, we have some conclusion. Our method have a few conflict with the CATA method, and we believe this is because prioritization of the basic needs in our approach may to avoid conflict at the formation planning stage. For the scalability and complexity experiment, we just design 4 kinds of the experiment. And as you can see, the 4 robots, 1 task, 10 robots, 2 tasks, and 15 robots, 3 tasks, and 20 robots, 4 tasks. And through this experiment, we found out if the task complexity is higher in some specific scenario, or the environment is more unstructurable and unpredictable, the individual agent will spend more energy and time in the communication to fulfill the task. The other is the full distributed communication graph sometimes is inefficient in a large-scale system of the coordination robots. So for the next impact of the different priority law at different level experience, The individual represents various behavior causing the system to displaying distinct performance. As you can see, also different kind of the priority. The group system just also have a different kind of behavior and a different kind of performance. So we also shelved the task priority to simulate the variations in the third level of the needs hierarchy. As you can see, we just consider different task priority order, and the group also represent a different kind of the performance and behaviors. And through this experiment, we figure out in the practical applications, an intelligent agent might dynamically change their needs and motivation according to the situation, especially in the adversary and unpredictable environments. So for the dynamic multitask assignment, the first experiment that we consider used different priority and 20 robots implementing the 1+1+1 scenario. And as you can see, the 3 tasks just assign, follow some sequence, and the task just assign dynamically, and the whole system represent a different kind of the behavior based on different kind of priority law. The second experiment that we just evaluated the impact of the conflict in negotiation process by comparing the energy cost of the 3 different tasks with and without considering conflicts. And as you can see, if we do not consider the conflict between the each agent, the whole system will finish the assignment pretty quickly. Yeah. So for the conclusion part, so our work just introduced a novel SAS as a framework for cooperative heterogeneous multi-robot system in dynamic task assignment and automate planning. It combines the robots' perception, communication, planning, and execution in multi-robot systems, which consider individuals' robots' needs and action plans. It emphasizes the complex relationship created through the communication between the robots. Specifically, we propose the robot needs hierarchy to model the robot's motivation and offer a priority queue in a distributed negotiation and agreement mechanism, avoiding planning conflict efficiently. Then we provide several alternate operations to decompose the complexity tasks into a series of simple subtasks. So for the future work, we, it would be worth investigating whether what if the different robots consider different needs and priority, and how the global performance can be achieved in such systems. And we plan to optimize the communication architecture and add the decision and learning level into the individual robots needs hierarchy to complete our robots needs model. So actually, implementing our work in the real robot, especially multi-robot system, is also very challenging and exciting work for our future research. So that is our papers. Thank you very much for our work.